Welcome to the first online lecture in which we will be covering the topic retaining walls. Here we will cover the design of reinforced cement concrete retaining walls and the structural behavior of different categories of retaining walls. So let's begin. Retaining walls are those types of structure which are primarily used to support and prevent the sliding of any loose earth fill or backfill, which can be made of loose soil or rocky material. The retaining walls can be of varying heights depending on the elevation of the backfill which we have to support. The backfill can be of further different types, like the soil which is in the backfill can be wet or dry, or can consist of different layers of different types of soils. The backfill can be horizontal, vertical, etc. So there are different cases of backfills which you have covered in your previous courses like geotechnical engineering and foundation engineering. I will be discussing in brief about those later on. So as you must have seen different types of retaining walls around your surroundings depending on different applications. Like some of the retaining walls are provided around on the sides of roads or highways. Some of the retaining walls are provided on the underhill or on the upper side of any building. Some of the retaining walls are provided to support the backfills in leveled gardens or for landscaping also. There are some other photographs of retaining walls. As you must have noticed, there are different types of materials which can be used for retaining walls, like stone masonry, plain concrete or reinforced cement concrete also. Sometimes cement concrete blocks can be also used as retaining walls. Depending on the site conditions, we choose the type of material which we will be using for making the retaining walls. So before moving on further, I'll be explaining you some of the terms related to retaining wall. So first is retained earth, which is the most important parameter for retaining wall, which is also known as backfill or earth fill. This is the portion which the retaining wall has to support, which consists of different types of soils having different types of properties. So this is the very important part of the retaining wall, which will influence the loads and the pressure acting on the retaining wall, and ultimately it will affect the design of retaining wall also. The second important term is angle of repose, which you have studied in your previous courses. It basically highlights the property and shear strength of the soil which is being held in the earth fill. Next is the surcharge. Surcharge is basically the vertical load which is present on the upper side of the retaining wall here. For example, if you are providing a retaining wall on the downhill side of a pavement or a road, then the surcharge load will consist of the dead and live loads being acted upon on the pavement by the traffic and by its dead weight itself. So that will contribute to the surcharge load, and the surcharge load will indirectly affect the lateral earth pressure which is acting on the retaining wall. So we will be discussing the surcharge load later on in some of the questions. Now next comes the retaining wall itself. The retaining wall has different components. This part, vertical part, which we usually visualize, is the stem, vertical stem of retaining wall. The front face of retaining wall is visible to us, and this is the back face or rear face which is on the backfill side. Usually the back face is slightly sloped and the front side is vertical or straight. Sometimes the front side can be provided in steps, as you must have seen in high retaining walls provided along the sides of highways or roads. Of retaining wall is sloped to achieve economic design of the retaining wall. The below bottom portion of retaining wall is the base slab, in which the portion which is on the backfill side is known as heel slab and the portion on the front side is known as toe slab. These are the drainage holes which are provided at different heights of retaining wall so as to accommodate the water passage from the backfill to the front. Now next is the different categories of retaining walls. So there are different categories of retaining walls depending on the type of material and on the basis of the structural behavior of the retaining wall. On the basis of material, we have stone masonry, concrete block masonry, plain concrete and RCC retaining walls. And on the basis of structural behavior, we have gravity, cantilever, counterfort and buttress retaining wall, which we will be studying in the coming slides. So first is the gravity retaining wall. The gravity retaining wall is the most basic type of wall which is constructed for quite low heights, that is up to 3-meter high backfills. The design of gravity retaining wall is quite simple and it is generally made up of massive stone masonry or either plain concrete masonry. The basic design philosophy behind the design of gravity retaining wall is that the weight of retaining wall is sufficient itself to provide stability against the pressure exerted by the backfill. This is the pressure exerted by the backfill on the retaining wall. This pressure is causing failure or may cause failure to the retaining wall. The retaining wall and its different components provide stability against this pressure and hence provide any type of failure in either the backfill or in the retaining wall itself. So these are the different types of gravity retaining walls: masonry units, stone or plain concrete. But as I repeat, these retaining walls are provided for less high backfills, that is up to 3 meter. Now next type of retaining wall is cantilever retaining wall. This is very important and most commonly used RCC retaining walls. As you can see in this particular diagram, this is kind of inverted T shape retaining wall. This is the backfill which this retaining wall has to support. It is generally made of RCC and is used for walls or backfill up to a height of 6 meters. It is quite economic for these heights and provided where gravity retaining walls cannot be provided. So first and foremost is why these walls are known as cantilever retaining walls. As you all know, the cantilever is that structural element which is fixed at one end and free on the other end. So in this type of retaining wall, all the individual components of cantilever retaining wall behave as cantilevers. This is a cantilever retaining wall, this is the stem, this is the toe slab and this is the heel slab. If we visualize these components separately, the stem of retaining wall is supported at this end and free at this end. So this behaves like a cantilever. Visualize this heel slab. This heel slab is fixed at this particular end and free at this end. So this is also a cantilever. And the toe slab is fixed here and free here. So this is also a cantilever. Hence all the individual elements behave as cantilever. Hence this is a cantilever retaining wall. Lateral pressure resisted by the backfill. Weight of earth on backfill and weight of retaining wall provide stability. In the previous gravity retaining wall, we studied that the weight of the retaining wall itself is sufficient to stabilize the earth pressure. Now in the cantilever retaining wall, the weight of retaining wall, the weight of backfill will provide stability against the lateral earth pressure acting on the wall. So these two diagrams are showing the reinforcement in the cantilever retaining walls. As you can see here, these lines are depicting the reinforcement in stem, heel slab and toe slab respectively. These arrows are depicting the different types of forces acting on the cantilever retaining wall. We will be discussing these after a few slides, but for now this is the surcharge load. This is the inclined earth pressure which is acting on the wall. It is inclined because of the inclined backfill. This is the upward soil pressure from the soil below the retaining wall. The individual cantilevers, that is stem, toe slab and heel slab, are provided with the reinforcement. We will be discussing the location of the reinforcement in detail later on. This is a sample example of a detailing of a cantilever retaining wall showing the reinforcement in stem, in heel slab, in toe slab. This is the cross section and this is the L section. This is the L section of the wall showing the vertical reinforcements. The main reinforcement in the stem is the vertical reinforcements, as you can see, and these dots, these are showing the lateral horizontal reinforcement in the cantilever retaining walls. We will be discussing while we will study the design of retaining walls later on. Now, next type of retaining wall is counterfort retaining wall, which is almost similar to the cantilever retaining wall, with the one major difference, which is, as you can see here, on the back side, that is on the backfill side, this is the backfill side, the triangular slabs are provided along the length of the retaining wall at a particular interval. This is first counterfort and this is second counterfort. The basic principle for providing these counterforts are to divide whole of the stem and whole of the heel slab into small segments. For example, this is a whole stem, length of the whole stem. We are dividing into 1, 2, 3 different segments. But will this result in? This will reduce the bending moments and shear forces acting on this particular stem. Similarly, in the heel slab also, this whole heel slab has been divided into different segments as seen here. So this is quite economic section when we are dealing with very high retaining walls, because if we use cantilever retaining wall for heights greater than 6 meter, the length of the as the length of the backfill is very large, the thickness of the stem will also come out to be very large and the reinforcement will also come out to be very large. Hence this will be quite uneconomic. Hence counterforts are the best solution for that. So these are also different pictures showing different types of counterfort retaining wall. In this particular three-dimensional diagram, you can see the reinforcements in the stem and in the triangular slabs, that is counterforts also. Please note that the counterforts are not visible on the front side. These are provided on the backfill, which is hidden beneath the backfill. This is a sample detailing of a counterfort retaining wall. Wall is the buttress retaining wall, which, as you can see in the diagram, is almost same as a counterfort retaining wall, but note a very big difference. These dots are showing the backfill, and in counterfort retaining wall, the counterforts were provided in the backfill side, not on the front face. But in buttress retaining wall, the counterforts are provided in here. These are known as buttresses, not counterforts. These triangular slabs are provided on the front side and not the back side. So this is the back side and this is the front side. So buttresses are visible to us on the front side. Buttresses are usually not preferred because they occupy space in the front of wall. This much space has been unutilized and cannot be utilized for any purpose. So buttresses are generally avoided in case of retaining walls. So these are the different types of retaining walls which we discussed: gravity retaining wall, cantilever retaining wall. Kindly note the differences visually here. This is a this is a gravity retaining wall without any heel slab or separate toe slab. This is a cantilever retaining wall with separate toe and heel slab. Hence, the weight of earth backfill is also providing resistance or stability. These are the counterforts provided on the backfill side. This is the backfill, and these are the buttresses provided on the front face. So this is the front face and this is the back face. So these are the four types of retaining walls. We will be doing the design of cantilever and counterfort retaining walls in detail. Buttresses are designed in similar way as counterfort retaining wall, with the difference that backfill pressure is not acting on the buttresses, as it is quite visible from here. So now next portion is very important, that is the forces acting on retaining wall. Before designing any type of RCC structure or any analysis of any type of structure, we need to know what are the different forces acting on it. So these are the different forces acting on retaining wall: lateral, vertical upward forces and vertical downward forces. This is the most important force on the basis of which the retaining walls are designed. Vertical upward and vertical downward forces are the consequent forces due to the provision of retaining walls. So the lateral force is the earth pressure, due to the earth pressure acting due to the backfill on the retaining wall, earth pressure due to the surcharge load, and passive earth pressure due to the earth fill on toe slab. Here, as you can see in this diagram, this is a cantilever retaining wall acted upon by, this is the active lateral earth pressure inclined. This is the passive earth pressure here, which is acting on the front face. You must have studied the difference between active and passive earth pressure in your previous classes. Active earth pressure is the dominant one due to the high backfill. Passive earth pressure is usually ignored in case of the retaining walls. So these are the lateral earth pressures. Next is the vertical upward forces. So on a retaining wall, only one vertical upward force acts, that is the soil pressure acting from beneath soil surface of the retaining wall. This is also a very important load. Next is vertical downward forces. These vertical downward forces are all the weights acting in and around the retaining wall. Like this is the weight of soil, weight of all components of the wall. This is the weight of stem. There will be the weight of slab. So these all will contribute to the forces acting on the cantilever, on any type of retaining wall. Also note, there is another type. This is the ground level on the front side, so there will be also this amount of weight acting on the front face, which is usually neglected because it will be quite low as compared to this weight as it is visible. So these are the different types of forces acting on the retaining wall. Line force is being divided into two components, that is horizontal and the vertical component. Here the role of both these components will be slightly different in the stability of the retaining wall, which we'll be covering in the coming portion. So these are the different forces acting on the retaining wall. Let us repeat: the lateral earth pressure due to active earth pressure and passive earth pressure. Passive earth pressure is generally neglected. The upward soil pressure acting on the retaining wall, and the downward weights of the backfill above heel slab, the weight of the front fill above the toe slab, which is the earth located below the ground level on the toe slab, and the weight of different components of retaining walls. So these all forces have a combined action on the retaining wall and will influence its behavior. So as I have stated earlier also, the most important force, which is the lateral earth pressure force in the retaining walls. You can easily calculate the weights of retaining wall and weight of the backfill, but the lateral earth pressure has to be calculated separately before designing the retaining wall, because due to this lateral earth pressure the retaining wall will have maximum amount of failures. This is the only primary force which will contribute to the failure of retaining wall. So this portion you must have covered in foundation engineering, but I have also added here because this is very important. Before designing or analyzing any type of retaining wall, you need to calculate, very important, you need to calculate yourself the lateral earth pressure acting on the retaining walls, which is P, capital P. So just a quick revision of this lateral earth pressure. So if a retaining wall is supporting a backfill, the backfill will obviously provide a lateral active force on this particular retaining wall, as this is called active earth pressure when the wall has a tendency to move away from the backfill like this. This you must have covered earlier. So this is active earth pressure, and on the front face where the retaining wall is below the ground level, the retaining wall has a tendency to move towards the backfill like this due to this particular soil here. So this is the passive earth pressure and this is the active earth pressure. So we are basically concerned about the active earth pressure because it will have the deterioration or detrimental effects on the retaining wall and will contribute to the movement or other types of failures in the retaining wall. So as the calculation of the earth force is very easy. This is the earth pressure and this is the earth force, lateral earth pressure and lateral earth force. So if there is a retaining wall of height h meters, the earth pressure will slightly increase as we travel below due to the effective stress principle, which you have already studied in Geotech 1. The effective stress on any particle on soil keeps on increasing as you move below. So this is here the effective stress or pressure will be 0 and here it will be maximum, which is K naught gamma h, where K naught is the coefficient of lateral earth pressure, gamma is the density of soil and h is the height of retaining wall. So this is K naught gamma h, this is h. So this is the lateral earth pressure. If we have to find the force acting on this particular portion, the force acting on any particular portion is pressure into area, and area of this triangle will be half into base into height. So half into base is K naught gamma into h, which will come out to be half K naught gamma h square. So this is the basic formula for calculation of lateral earth pressure, which is P. Although this P can be different in different situations, which we will be covering in the coming slides. We calculate the lateral earth pressure and forces for active case and passive case as discussed earlier. In retaining walls we have two cases, that is active earth pressure on the backfill side and the passive earth pressure on the front side. So lateral active earth pressure, the earth pressure at the base it will be maximum. It will be Ka into gamma h. Kindly note here I have written Ka because this is the coefficient of active earth pressure. Gamma is the density of soil backfill and the h is the total height of retaining wall. From this pressure we will calculate the force, that is pressure into area. Area is half into base into height, so half into Ka gamma h square as discussed in the previous slide. So this is the lateral earth pressure diagram for this particular retaining wall, and this is the lateral pressure and this is the lateral force. And as we all know, in a triangle the lateral force acts at at its centroid, that is centroid of a triangle, which is at a distance of h by 3 from base. So the lateral earth force acts at a distance of h by 3 from the base of retaining wall, and its value is half Ka gamma h square. Similarly, same will be for passive earth pressure. With the minute difference, in place of Ka we will have Kp, and in place of capital H, sorry, I have written here small h, this, if this is h small h, then Pa is equal to Kp gamma into small h, and this will be, sorry, another mistake, this will be Pp. This will be the lateral passive earth pressure, and lateral passive earth force will be the area of triangle of this, which will be half Kp gamma into h square, where gamma is the density of soil present here, h is this height. So these are the two types of earth pressure, active and passive. So why are we doing this? We are least concerned about Pp because passive earth pressure is quite low due to quite low height and it can be neglected. We are basically concerned with Pa. If you know the soil characteristics, you will know its gamma. H you will know if you know the height of the backfill, which you will always know. And this is the most important part, which is Ka, coefficient of active earth pressure. So as you have studied earlier also, the Ka depends on different cases, and for this we will be using different types of lateral earth pressure theories like Coulomb's wedge theory and Rankines theory, and any of these can be used to find this Ka or Kp or Pa or Pp. So we will be discussing both of these. So now concentrate, as we will be discussing different cases. This is the most ideal case, simple case for a retaining wall, that is horizontal backfill with a same type of soil here. So the formula for Pa is quite simple, half Ka gamma h square. But if there is any complicated case, for example the soil is saturated and with water, and there are different layers, this is soil 1, this is soil 2, this is soil 3, so this will complicate the expression for Pa also and Ka also. So now we will be studying the different cases for Coulomb's as well as Rankines. You can use any of these methods to calculate the value of Ka. The most commonly used theory is Rankines theory, but you can use any of the above. So now first we will calculate the coefficient of lateral earth pressure by Coulomb's wedge theory. I hope you remember this formula. If you don't remember, you can see your geotechnical books you studied in the previous course of foundation engineering. Here we are concerned, as see in the previous slide, we are concerned with calculating Ka. So Ka is sine square alpha plus phi, sine square alpha, sine alpha plus delta, and this whole expression, where K is the coefficient of active earth pressure, phi is the angle of internal friction, which is depending on the type of soil, beta is the angle of backfill slope. Angle of backfill slope means this is your retaining wall, this is the backfill. So this backfill can be horizontal, the backfill can be inclined also, like this. So here the angle will be different. So this is the angle of backfill slope. Angle of friction between soil and wall. The angle of friction between soil and wall will depend on the type of interface, that is the type of material of the wall, which is usually taken as 2 by 3 to 1 by 2. Next is the slope angle of wall, which is measured from horizontal. This I will show you from the previous slide. So here, as you can see, this angle is not 90 degree. The slope angle of the wall with the horizontal, this is more than 90 degree for this particular wall, and for this particular wall this is 90 degree. Hence this angle can also vary. So depending on the angle, whichever angle we have, this is will give you value of alpha. If that is vertical, we will give it 90 degree. So this is the generalized equation for calculation of Ka according to Coulomb's wedge theory. But this formula will be used primarily when you have all these angles, different angles, that is you have different beta, there is no horizontal slope and there is some particular angle of friction and the slope angle is not 90 degree. For a simpler case, which is usually given, which may be given, so for the case of horizontal backfill, considering zero friction, that is no friction between wall and the soil. So if we are having horizontal backfill, then beta will be 0. If there is no friction, then delta will be 0, and the soil side wall is vertical, that is alpha is 90 degree. So if we substitute all these values here in this particular equation, the equation will reduce to Ka is equal to 1 minus sin phi upon 1 plus sin phi, where phi is the angle of internal friction. So if you do not have any complicated case, you can use simply this formula. But if either of these values, that is angle of backfill slope or delta or alpha, is not any of these, you will have to use this formula. So this is the coefficient of lateral earth pressure from Coulomb's wedge theory. Now the same we will calculate from Rinkin's theory. There are complicated derivations for these which we will not cover in this particular course, so you just need to have the idea of this formula. Obviously you can refer the books from your previous subjects so as to know how these formulas have been derived. So from Rinkin's theory, the formula is slightly different. Kindly note the changes, slightly different. So this is the formula, K is cos beta minus cos square beta minus cos square phi, something like this, where beta is the backfill slope angle and phi is the internal angle of soil. Note here that the friction between soil and wall is not considered here. So this formula will be using when there is inclined backfill. If there is horizontal backfill, then beta will be 0, hence horizontal backfill के लिए beta is 0, so Ka will come out to be 1 minus sin phi upon 1 plus sin phi, which is same as in the case of Coulomb's wedge theory. So either you use Coulomb's or Rinkin's, the formula you will get the same. Similarly for Kp, that is the passive earth pressure, the formula you will derive, and finally you will get this expression Kp is 1 plus sin phi upon 1 minus sin phi, although as I have said before, the passive earth pressure is being neglected for design of retaining walls, so we will not be much using this. Now next is, so this is the basic formulas which you will be using. K is 1 minus sin phi upon 1 plus sin phi for kindly note, horizontal backfill with zero friction and soil slide wall. Other factors which can influence the value of Ka or Kp apart from the backfill slope or the presence of friction between soil and the wall or the slope angle of wall. So I have summarized and explained all these in the coming slides. So we have studied these cases, that is slide and wall parameters, which is backfill slope, friction between soil and wall, and back slope of wall. Backfill slope means the beta angle, friction between soil and wall means the delta angle, and the back slope of wall means the alpha angle. So apart from these, there can be variety of other soil parameters which can affect the value of Pa or Ka depending on the condition. So the backfill can be either dry, that is cohesionless, which is a very ideal case, usually not possible. Next is wet or saturated soil, cohesive soil. The main difference in these two will be, if there is a dry soil, we will use the dry unit weight, and when there is saturated soil, we use gamma saturated or the gamma submerged you have studied all these properties in geotechnical engineering. Next case is you can have different types of soils in layers in the backfill. Like there is a wall and the backfill is consisting of different layers of different types of soils. That is, this will have different gamma and this will have different gamma. So automatically if gamma is different, that will influence the value of PA. Next, water table at a particular depth. There can be a case where behind the retaining wall, this is the retaining wall and the backfill. So at a particular depth below the ground, the water table is present here. So this will be dry soil and this will be saturated soil. So obviously there is difference in the depth of backfill, so PA will be different. Similarly, there can be another case where all of the soil sample is saturated. So there will be two types of gamma here, gamma of your soil and gamma of your water. These you must have studied in effective stress principle, which in Geotech 1. And last is the surcharge load. If a vertical load is acting on above the retaining wall, so this will indirectly affect the value of PA. For this, a special case has been added. So we will be discussing one by one all these cases, although you might have covered these earlier also. So first case is for dry or cohesionless soil. So for horizontal backfill, if there is a cohesionless soil, there will be the value of Ka will be same and Pa will be half Ka gamma H square, no difference. If there is inclined backfill of cohesionless soil, that is inclined backfill or sloping backfill of your dry soil, then we will use the case for inclined backfill, which we have studied here. This is the case for inclined soil, inclined backfill. So you can use this formula. Note here that in case there is horizontal or sloping backfill, there will be only change in the Ka value, not the Pa values, which will indirectly affect the Pa values. Now next is submergence. When the backfill is fully saturated, lateral earth pressure will be due to the submerged unit weight of soil and lateral earth pressure due to pore water. This is your retaining wall and this is a dry soil with submerged unit weight, that is, it is saturated with water. So the earth pressure will have two components, that is earth pressure due to the submerged unit weight and earth pressure due to the pore water pressure. So these lateral pressure diagrams have been made according to the effective stress problems which you might have studied in the previous course. Below the surface, if we take any random point Z, the lateral earth pressure will be sigma, that is Ka gamma dash into Z plus gamma W into Z. Actually, if we make another diagram here, this is the total earth pressure acting in the bottom, which will be actually Ka gamma saturated into H. But this gamma saturated is basically of two components, that is the submerged unit weight of soil and the pore water pressure. So this will come out to be like this. So this is Ka gamma dash into H, where gamma dash is the submerged unit weight when will be saturated unit weight. So gamma dash is equal to gamma saturated minus your gamma W, which is the unit weight of water, and this will be pore water pressure, that is gamma W into H. So if you are having a case of submergence, lateral earth pressure will be triangular, but there will be two triangles here, not one triangle. So you need to find the PA of both these triangles and then resultant of whole this triangle. I will be giving you another lecture on this particular topic separately. Now there is another subcase of submergence. Here in this case the whole backfill was saturated, and here in this case there is a moist sand and there is saturated sand. That is, so this is Ka for this particular portion. There is actually the soil is of different types here, so Ka gamma into H2, and after that there is Ka gamma dash into H1. As this is the saturated sand, the value of earth pressure will be Ka gamma dash into H1 for this particular portion, and in this portion we have water also, pore water pressure, so gamma W into H1. In this portion we have no water, so we will just have the dry unit weight, that is gamma, or moist unit weight, which might have been given in this particular problem. So you will get this lateral earth pressure diagram, which is not at all a particular triangle. So what we will do, we will divide this particular diagram into different portions. For example, this is a triangle, this is a first triangle, this is a rectangle number 2, this is a third triangle, and there can be another fourth triangle, which is this one. So we will calculate the earth pressure in P1, P2, P3, P4. We will calculate the earth pressure force, that is earth pressure here is Ka gamma into H2 into, this is the earth pressure, and the force will be half into Ka gamma H2 into height, that is H2, so half Ka gamma H2 whole square. So this will give you P1. Similarly, P2 is a rectangle, so the area of this rectangle is Ka gamma H2 into H1. So Ka gamma H2 into H1 will give you the P2. P3 will be half Ka gamma dash H1 into H1. P4 will be half Ka gamma dash H1 plus gamma W H1 into H1. So you will combine all these forces P1 to P4, you will get the final force P, and after that you will have to find out the resultant of all these forces using the method you used in engineering mechanics, where you have different types of forces acting here, in this particular in a particular area, and then you will have to find out the centroid of all these forces together for a resultant force. So you will use the moment area method. For that I will be giving you another lecture. So you will find out individual forces and the final resultant force P, and the location of this resultant force P, which will be used in the design of retaining. Another case, that is apart from these two cases, that is a backfill having different types of soils in layers, soil 1, soil 2, soil 3, having different gammas, gamma 1, gamma 2, gamma 3. So as discussed here, the lateral earth pressure diagram will also be something like this for this particular case, and then we will divide those diagrams into individual sections, and then we will calculate the total resultant P and its location. The next case is the uniform surcharge. Surcharge is basically vertical load acting on the backfill soil above the top of the wall, like shown here. It can be either dead load or live load, which could result from highway or parking lot, paving or adjacent footing. There can be any case here. For example, if a building is situated here, so its dead load of its footing will be part of the surcharge load. Usually the surcharge load is given if there is a case of that. So due to this surcharge load, there will be additional earth pressure acting on this particular soil. Like note here, if you forget the surcharge load, the actual lateral earth pressure diagram will be this triangle with lateral earth pressure P acting at a height h by 3. So this is the case which we have discussed in all previous slides. If there is a surcharge load, an additional load will act here, that is Ka into W into H, which is shown here. If you can see this rectangle, this whole rectangle, this is the additional lateral earth pressure which will act throughout the height of this particular backfill, where W is the surcharge load and H is the height of your backfill. So very simple. If you have any surcharge load, your diagram will be slightly modified as shown here. So there are I have included some examples on lateral earth pressure which I discussed before also. This is a retaining wall having surcharge load with dried soil here and water table here at this point. So obviously the soil below will be saturated and this will be dry. So we will make the lateral earth pressure diagram as using the effective stress questions using which we have already studied. So first of all, due to this surcharge load, we will have an additional pressure acting on this particular wall, additional earth pressure, which will be K into Q. Okay, so this is K into Q, which is the additional pressure acting on this particular wall. Note here, right now I'm concerned only about pressure, which is K into W, K into Q here. If you multiply it with H, it will give you the force. So this is the first, you will draw the rectangle showing Ka, K0 into Q. Next, for this particular portion, there is no moisture, or there is no saturation or submergence of soil. So the value of pressure here will be K into gamma into H1. So total will come out to be K into Q plus K into gamma into H1, which they have written here in particular first in a single equation. Below that we have saturated sample. So as you know, for saturated sample we divide into two portions, that is the submerged unit weight and the water pressure. So this will come out to be K into gamma dash into H2, where gamma dash is the submerged unit weight, plus K into gamma W into H2, and obviously plus we will have the additional load which are coming from above, that is K0 into Q plus K0 into gamma into H1. So this will be the complete diagram. Here we have divided this particular diagram into 5 components. This is a rectangle, this is a triangle, this is a rectangle, triangle and another triangle. So we will calculate P1, P2, P3, P4, P5 and get the desired value of resultant P. And this is of a retaining wall having 3 layers of different types of soils, having different soil parameters gamma 1 51, gamma 2 52, gamma 3 53. Gamma 1 will have influence on Ka1 because Ka is 1 minus sin phi upon 1 plus sin phi. So here the earth pressure at this location, this depth will be sorry, Ka1 into phi 1 into whatever this height is. Similarly, at this location the value of pressure will be Ka1 into gamma 1 plus Ka2 into gamma 2 into H2, whatever this height is. Similarly, we will calculate the pressure at this particular depth having parameters gamma 3 and phi 3. So after that we will join these with lines. As you can see, these are having different lengths depending on the values. You will have to draw according to scale, somewhat according to scale, because some values may be larger, some may be smaller. Now we will have to calculate individual values of these PA pressures in this and this portion. So you divide whole of this area into three areas. First is this triangle, second is this trapezium, and third is another trapezium. So area of this triangle will be half into base into height. Area of trapezium is half into sum of parallel sides into this height. And next is area of this trapezium. You add all these areas PA1 plus PA2 plus PA3 to get the total resultant value PA, and then you find out the location of resultant from base of wall. Okay, so you will have to assume the location of PA, that is at a distance Z, and then from this equation, which you have used many times since your first or third semester, so you will find out the location of the resultant force.